Hey folks, Mrs. White here, coming at you with our second section from chapter 6. Section 6.2 is going to have us solving exponential equations today. Last time that we were looking at some topics here, we were looking at graphing exponential equations. So we are going to review graphing. I have a pretty complicated looking one here, and we'll make our little table and we'll give that a graph. And then we're going to hop right into how do we go about solving. So again, this is section, sorry about that, 6-2. We're going to solve two together. We're going to develop steps after I do one of them. Okay, so I want you to be thinking about what work are we doing to be able to solve this. And then I'm going to have you try two on your own. I will put up my work, but I'm going to make it go through reasonably quick. Then the bulk of our time, even though the solving is important, okay, because we're going to do lots of different types of solving in this chapter, we are also going to take a look at some word problems, because what's really cool about exponential functions is that they're super duper duper applicable to the real world. And I know I started off this chapter by talking about like the zombie apocalypse situation, right, as a word problem. Well, it ties into a lot of stuff that happens in the real world, this exponential curve, including compound interest. So we'll talk about compound interest also. Your homework tonight is about 11 problems in your ebook. 9 through 15 is 7 problems. 6 of those are straight up solving. One of those is like what we're going to do here, where you have to write it. And then the following 4 are going to focus on compound interest, because again, compound interest is how banks do stuff. Okay, that's how much they learn, or how much they figure out or calculate what to charge you, or maybe interest that you actually receive by opening a certain type of account. So I do want to make sure that you practice a handful of those problems and see how they work. And that's what we're going to be doing today. I don't know if you noticed online, but I did attach a note-taking guide, which has not the sit and begin, but it has some of the other stuff in it. You're welcome to use that if you'd like to. I also attached a document that has a screenshot of the answers to the homework, because I know word problems are your least favorite. And I thought that if you knew at least if you got the correct answer or not, you would know whether or not to attend office hours and ask some questions, okay? Versus just being like, I don't know if I did it right or not. I want you to know, okay? Again, in these flipped lessons, I'm not going over homeworks, okay? That's an opportunity for you to learn new stuff in these lessons. It is not a time to be going over those homework problems necessarily. So please, 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 over the next month, attend those office hours if you need to. I'm also going to do another plug, as long as Mrs. Boyce is fine with it, and I'll talk to her this afternoon. My goal would be to allow you folks to have one side of a 3x5 card or one side of a note sheet to use on this test. Chapter 6 is huge, okay? And I think I mentioned it last time that we had a lesson. So I feel like it would be a lot to expect you to memorize at home without me being there explaining stuff, without you being able to, consistently ask questions. That doesn't mean you're going to get 100 on the test. You folks know that, okay? It's a hard exam. That's why I'm offering you to have some notes to use on it. So what that means is you may or may not be taking good notes during these lessons. I would encourage you now to take some really good notes over the next couple weeks so that you knock it out of the park at the very end of the school year when we take our test on chapter 6. We have no final. We're just going to be taking a test on it, and it has like a lot of sections, like 9 sections. So please, please, please consider taking some good notes now so that you can just reference them and summarize them on a note sheet that you'll be able to use on the exam. Okay? So there's a plug for that. Take some good notes. Please, please, please. It will benefit you. So now let's do a quick little review of how do we go about graphing these exponential functions. Okay, now I want to remind you that there's 2 types of exponential functions. You have an exponential growth that looks like this, or you have an exponential decay, which looks like this. So it's steep and then it slows down. Here it's slow and then it gets really steep. So the way that you determine this is not by a negative necessarily being applied somewhere. It is with your growth factor. So this is what we multiply by every time when we raise something to a power. And if this growth factor is greater than 0 but less than 1, that means it's actually going to be a decay factor. So because this is 1/5, and I know that that is less than 1 but greater than 0, that means I'm going to be dealing with a graph that looks a heck of a lot like this. And that was one of the 2 Khan Academy skills I asked you folks to work on for class today. So to graph this, I know the general shape is going to look like that. I need 3 points. So I'm going to make my little XY chart. But I don't just pick any x's willy-nilly. I'm going to look at my exponent, x plus 5, and I'm going to set that equal to 3 values. I'm going to set it equal to the exponents that are easiest to work with, which are -1, an exponent of 0 because it will equal 1, and then an exponent of positive 1 because that means that your base will stay exactly the same. Okay, so let's solve for each of these. So I'm going to minus 5, which gives me a negative 6. That'll be one of my x values. I'm going to minus 5, which will give me negative 5, and minus 5, which will give me negative 4. So I'm ready to plug those values in and get out some other values. So if I put a negative 6 here, I end up with negative 6 plus 5 is negative 1. And if you recall, anything to the negative 1 power means change its location. So this 1 to the negative 1 would go in the bottom. This 5 to the negative 1 would go in the top. So this actually is going to become the reciprocal, which is 5. So I will have 1/2 times 5 over 1 plus 8. Okay, that's because, again, this was negative 1. 1/5 to the negative 1 means change their locations. So I end up with 5 over 2. Which is the same thing as 2.5, and 2.5 plus 8 is going to be 10.5. I'm ready to plug in my next value, which is negative 5. So negative 5 plus 5 is 0, and anything to the 0 power is 1. Okay, that was one of our exponent properties. So I technically have 1/2 times 1 plus 8. Well, 1/2 times 1 is 1/2, and 1/2 plus 8 is 8.5, or 8.5. My last point that I'm going to do is going to be to plug in negative 4 here. Okay, negative 4 plus 5 is 1. So that gives me 1/2 times 1/5 to the first power, which is just 1/5, plus 8. So I go across the top and across the bottom, and I get 1/10 plus 8, or 8 and 1/10, which is the same thing as 8.1, right? That's 1/10. Now I'm ready to graph it up. My y's are, none of them are negative, so I'm not going to even include that. I don't even really need to include the positive x's, right? I'm going to start down at negative 6 and then negative 5, negative 4. So 1, 2, 3, 4, 5, 6. And then, wow, these numbers get big, right? Which makes sense because if you remember, our shift up is 8. In fact, that reminds me, I forgot something really important. I need to decide where my asymptote is. That's what I should have done first. See, I forgot. Okay, my asymptote is going to be, instead of it equaling x equals 0, or y equals 0, excuse me, it's going to be y equals 8. It's going to be shifted up 8. So 1, 2, 3, 4, 5, 6, 7, 8. Here's going to be my asymptote. It's going to get really darn close to that line, but never hit it. And then I'm going to go 9, 10, 11, 12. Why not? It makes me feel good. So I'm going to go over to my negative 6 and up. Here's 8, 9, 10.5. I'm going to go over to negative 5, which is right here, and then I'm going to go up 8.5, so right about there, maybe even a little smaller. And then I'm going to do my last point, which is over to negative 4, 1, 2, 3, 4, and I'm going to go up 8.1. So you can see it's already getting really darn close to that line. And here's that exact exponential decay that I was anticipating, right? It's kind of whoop, and it's going to get really close to that line, but it's never going to hit it, and this is going to increase exponentially, right? It's exponential decay. Boom, there you go. They're not really going to get harder than this, right? Figure out where your asymptote is, figure out your XY chart. And these are the items you would need. Perfect. Hopefully that felt okay to you. If not, I'm happy to go over that during this week's office hours also. Nice little review. So now let's start talking about solving exponential equations. So I have this available to you folks with the answers and everything. Again, I don't really care if you see the answers. It's about the process. So I'm going to just solve this one for you, and then I'll talk you through what I did. And then I'll talk you through these steps, and then we'll actually write out what the steps are here to the side, and you can give them a go applying them to these two problems below. So I'm going to be quiet, but I'm going to solve this somewhat slow right now. You know what? I don't think I'm going to be quiet. I'm going to talk you through what I'm thinking. So in a perfect world, because x, the variable that I need to solve for, is in the exponent, I would want this value to be x, right? I would want to be able to say, okay, 2 to the x is the same thing as whatever the power is over here. Now, the reason why I can't say x equals 3 is because these two bases are different, right? Well, if those bases were the same, then I'd be able to take whatever number is here and say that that is what equals x. So that's what I'm going to do, okay? I'm going to try to rewrite the number 8 as a base 2. So I still have a 2x over here, and I know what I said is tricky, but hopefully it will make sense after I do it. I know that if I think of the factorization of 8, okay, the prime factorization, it can be 2 and 4, and 2 and 2. So really, 8 in its factored form would be 2 to the 1, 2, 3 third power, okay, 2 to the third. And hopefully that's very familiar to you, right? 8 equals 2 to the third. So I could write this, instead of putting an 8 here to the third, I could have a 2 to the third, because it's equivalent to 8, raised to the third again. Okay, so again, 8 equals 2 to the third, so I could replace the 8 with a 2 to the third. And then I still have this third on the outside, I have to keep it there. Well, if we just wanted to simplify this side, right, because we want it to look like 2 to some power, I notice that this is a power to a power. Again, those exponent properties are coming into play all the time. When you have a power to a power, you should take those two numbers and multiply them. So this is the same thing as 2 to the 3 times 3, which is 9. So take a look here. If 2 to the x equals 2 to the 9th, then x has to equal 9. There's our answer, okay? So let's do it again over here. I'm going to look. I have a base of 9 and a base of 3, and I notice my x, wow, that's in both of them. This one feels really darn tricky. But the best situation would be that I get the same bases, right? And then the bases just cancel out, and I'm left with x minus 9, or just exponent equals exponent. So here, I want these two bases to be the same, and I notice 3 is already prime. But 9 is not. 9 can be broken into 3 times 3, or 3 to the 1, 2 second power. So I could rewrite this as, instead of 9, 3 to the second power, raised to the 2x minus 1 power, right? Because I'm just rewriting the 9 only. I'll just copy this back over. Now, when I have a power to a power, it means that I need to multiply. So when I multiply these, it's a mono times a poly. So I need to send the 2 here and here. So I end up with 3 to the 2 times 2x, which is 4x, and 2 times minus 1, which is negative 2, equals 3 to the 6x. And I am loving this right now because the 3's, they're the same base, so they're going to cancel. And I'm just left with 4x minus 2 equals 6x. And honestly, this is just a linear equation now. This is freaking awesome because I can solve this. I'm going to minus 4x minus 4x. I get negative 2 equals 2x. Divide by 2, divide by 2. I get x equals negative 1. Beautiful. Okay? So let's look at these two examples and develop some steps together. I know watching an example is nice, but it's also really nice in our notes to have the steps that we took. So the first thing that we had to do here is you're going to look at your bases. And you want to get the same bases. And you're going to get the same bases by factoring both. Okay, and by factoring, I don't mean factoring, I mean do like your prime factorization. Okay. So, for example, 8 was 2 times 2 times 2. I didn't leave it as 2 times 4, right? 2 times 2 times 2, 2 to the third. 9 was 3 times 3, 3 squared, okay? Now, if this was a 9 and this was a 27, I would have to do it to both, okay? Because 27, if you think about it, would be 3 times 9 and 3 times 3. So it would actually be 3 to the 1, 2, 3, third power. You need to potentially do both. Here, we only had to do one because this was already prime. Here, the 2 is already prime. We didn't have to worry about it with the 8, okay? So make sure you have the same bases. If you don't have the same bases, take a look at them, maybe do some prime factorization and potentially to both of them, okay? So after you have that, what's awesome is that your bases will cancel if they're the same. And then you're going to just set it up as exponent equals the other exponent. And then you're just going to solve for your variable by isolating, which is what we always do. Ooh, variable. There you go. You know what I'm saying, okay? So really, it's only 3 steps, but it can be tricky, right? Take a look at your bases, give them a little prime factorization. So what I want you to do right now is pause the video, go through, solve this, make sure you get 2. If you don't, that's fine. I'm going to go through and solve it myself. Go through this one. Okay, solve it. See if you can get 3. Don't worry if you don't, okay, because I'm going to show you in just a second. But seriously, pause the video and give these 2 a go. All right, so let's take a look at this first one here. Okay. First things first, I noticed neither of these were prime, so I did the prime factorization of both. Now, I do want to clue you into something. If you noticed that 64 can be divisible by 4 exactly 4 times, which I don't know, if you, not 4 times, excuse me, 3 times. So if you knew 64 was 4 to the third power, as long as the bases are the same, that's fine. Okay, so I could have had this equals 4 to the third power and then just canceled the bases from there. But if you do not recognize that, okay, that this can go evenly into this several times, then just do the prime factorization of both. So that's what I did here. It was a little bit more work, but it doesn't really matter because I end up with the same answer. Okay, so I wrote them both in their prime factorization form. They both ended up having a base of 2, which is what has to happen. They have to have that same basis. Then I said, okay, power to a power. I'm going to distribute this 2 across and get 4n minus 2. This one stayed 2 to the 6th. Bases canceled, exponent equals exponent, and then just get my n alone. Okay, so add 2, divide by 4, divide by 4. Give a go to 1b if you haven't already. So let's take a look at this last one, okay? I noticed my 5 was prime, but 125 wasn't, so I brought it over here. And I noticed it was 5 to the third. So I rewrote it as 5 to the third. Again, mono and a poly, so I distribute it, because when we do power to power, we multiply. Then, because they had the same bases, I could cancel them out, and then just get my x alone. Hopefully you're feeling like that's not too bad. That's 6 of your homework problems. The other 5 of your homework problems are word problems, which is what we'll take a look at now, okay? I understand that word problems are tricky for you. They can be tricky for me too, potentially. So all I'm saying is just take your time and do your best, okay? It's important that you see how these connect to the real world because exponential growth and decay always do. So Kristen starts an experiment and it has 7,500 bacteria cells, okay? And she's looking at how the cells multiply. So after 4 hours, there are 23,000 cells. So just after 4 hours, it increased a lot. So they're telling us it's exponential. So they're telling us write an exponential function that could be used to model the number of bacteria after X hours if the number of bacteria changes at the same rate. Now, we have not written any of these equations yet, but yesterday we were presented with this idea, y equals ab to the x. And we were told that b helps us define if it's a growth or decay function. This is actually our growth factor. And a, although you didn't realize it, is what your initial amount is. Okay? So that's kind of interesting. So if you start with, for example, if we're thinking about the zombie stuff, right? If you started with 3 people who randomly had it and it doubled every day, then you would have a 3 here, a 2 here, and then X would represent the amount of days that's passed, right? If it was 2, if it doubled every 2 days and your initial amount was 3. Okay, so it's kind of nifty. Once you know this, you can start doing word problems like these, okay? So they want us to write an equation. We know that this is where she started it, so this is going to be our A value. Now here's the dilemma. They do not tell us our growth factor, right? It would be nice if they say it doubles every hour, then you would put a 2 here and X would be amount of hours. Okay. Instead, it's telling us an amount of time. Okay. And it's telling us what it ended with, what the result was. So think about this for a second. If something ended, it's going to be our y, right? It's what all of this happened, and then this is what we got. So I'm going to plug each of these things in where I think they go. So if it ends with 23,000 cells, I'm going to plug that in for y. 23,000 cells equals, I know what I started with, right? They told me I started out with 7,500. They did not tell me my growth factor, whether it was increasing by 3 times every hour or whatever. I don't know that. So I'm going to keep that as my variable. And then I'm going to raise it to a power. Now the power here is actually not going to be X. The power is how much time has passed. And we know the time. It's 4 hours. So I'm going to put a 4 there. Now, you are going to need a calculator to go about and figure out our growth factors so we can actually write the equation. Because they're asking us to write an exponential function, which means our x needs to be here. So we actually need to find out b, substitute it back in, put an x here and a y here. Okay, so what we're doing is all we're doing right now is calculating our growth rate so that we can plug in our growth rate, plug in our initial amount, keep our y, and keep our x. So first things first, to be able to solve for b, I got to start getting it alone, right? Well, I got to get this gone. It's being multiplied. I'm going to start by dividing by 7,500. Divide by 7,500. Well, I'm going to cross off 2 zeros because that's how that works, right? This is gone, by the way. So I really have 230 divided by 75. I'm going to pull up a calculator. I got it right here. I have 230. That calculator is not going to work because it is not bright enough in my room right now. I'll use my phone. All right, pulling it up. I'm wasting your time. I'm sorry. Okay, it's up. So I'm going to do 230 divided by 75 equals 3.06 repeating. So we'll do 3.07 approximately, right? Because it's 0.6666666. Equals b to the 4th power. Now think back to when we were solving for squares, right? The opposite, if we would have had b squared here, I would have said, okay, well, we need to get rid of the squared. We're going to square root it. Now it's a b to the 4th power, so I'm not going to square root it. I'm going to 4th root it, right? 4th root and 4th power cancel. That means I have to 4th root over here, which is pretty darn complicated, okay? So I'm going to have what number times itself 4 times equals 3.07. So I'll calculate that on my calculator also. And I end up getting 1.323. Okay, so I'm going to leave it as 1.32 right now. Just so you know, what I did is I'm using my cell phone, and I turned it sideways. And to do whatever, like your nth root, I used this button, the square root of y. The yth root of x is what I'm trying to say, the yth root of x. So if we're looking at it this way, I type in my x first, I press this button, which is this whole thing, and then I type in the y after. Okay, and then I press enter. And that's going to give me the value that I just got, so 1.32 hot mess. So now I'm ready to write my actual equation. To get my actual equation, I am going to keep the y. I'm going to put my initial amount in, which is 7,500. I'm going to put my growth rate, which is 1.32. And then I'm going to raise it to the x power. When x, again, is the amount of time that's passed, specifically in hours, okay? And y is going to be the total bacteria after x amount of hours. So now that I have this equation, folks, I can do something with it, all right? Like having the exponential function means that I can calculate for any hours that I want now and figure out how much bacteria there should actually be. So we can go, along and answer part B now. So how many bacteria cells will be expected in the sample after 12 hours? So 12 hours is a measure of time. I'm going to plug it in for my x. So I currently will have y equals 7,500 times 1.32 to the 12. Now, some of you may say, well, if this is 4 hours, wouldn't I just triple it? Okay, so let me triple it and we'll see if that works. Because I'm assuming you're thinking that it's going to work. So after 4 hours, it was 23,000. Let's just times that by 3, which you may think 3 times 4 is 12. So potentially, it could be 69,000 bacteria cells. I'm going to tell you it's not going to work right now. And I'll explain why after, okay? So let's actually do this work. So I'm going to pull back up my calculator, okay? Use the one right on my phone. I'm going to make sure to be careful and use order of operations, okay? So the first thing I have to do is type in 1.32. And I'm going to raise it to the 12th power. Now, there's a little button on most calculators that looks like this. It's called a caret. So if I were to type in 1.32 and then the caret and then 12, it would, and press enter, it's going to do 1.32 to the 12th power. It looks to me like I don't have that button. Instead, on my phone, I have one that looks like X with a little Y. So I'm going to type in 1.32. I'm going to press my X to the Y power. button, and then I'm going to type in 12. And I get 27.9825. I'm going to round it to 0.98. I'm going to take that and I'm going to times it by my 7,500. And I get 209,869.0699. So I'm going to put 0.07. Okay. So after 12 hours, I had 209,000, not 69,000. So the reason why these don't match, folks, is because the error in your thinking is that you're thinking it's linear. You think that every time it's going up by the same amount. Boom, boom, boom. So from here to here and from here to here, it's going to be increasing at the same rate. And so you would think that you can just triple it or quadruple it or times it by 5. However, because it's exponential and it's actually growing like this, from here to here is very different than from here to here. Although it might look the same on the x, right? The change in height is very, very different. This is a huge difference versus just that little tiny bit. You cannot just take a value and double it or triple it based on the hours. In an exponential function, you have to plug in the new amount of hours and actually do that work because it is changing at a differing rate depending on where you are on this curve. It varies in steepness. Okay. Because this is a word problem, I should put a label on this. This represents the amount of bacteria cells, so I could label it as cells. So based on what we talked about here, and I know this is a lot, I totally feel you. I want you to give a go to the problem like this. Okay, I'm going to give you another one, and I want you to try for a minute or two, and then we'll go over it together. A manufacturer distributed 3.2 million aluminum cans in 2005. In 2010, the manufacturer distributed this many cans made from recycled cans that it had previously distributed. Assuming that the recycling rate continues, okay, so they're saying that the rate's going to continue. Write an equation to model the situation, model the distribution each year of the cans that are made from recycled aluminum. How many cans can be made or expected to be made in the year 2050, okay? So he had this many cans here. Actually, you know what? If you didn't already pause this and do this problem or try to, go for it. You can pause it at any point and keep going on your own and then come back to it if you need to, okay? Then we have a second year and we have a second amount, okay? So I want to ask you something. From here to here, did it increase or decrease? And hopefully you're saying to yourself right now that, heck yeah, it's super decreased, right? It decreased. Because this decreased, our growth rate should be less than 1, it is going to be exponential decay, right? So it's going to look like this, not the other way around. So you should notice that first. My question to you is, how much time has passed for it to go from 3.2 million to 420,000? Well, it took from 2005 to 2010. So our time frame is 5 years right now. It started with 3.2 million and it ended with 420,000. Do we know the growth rate? No, but we know it's going to be between 0 and +1, okay? Because it went down. It's an exponential decay. So we're going to plug in the values we know, okay? So we're ending with 400. I'm going to put this work over here and we'll keep it in pink. 420,000. Its initial amount was 3.2 million or 3,200,000. We do not know our growth rate. I'm going to leave it as B for, you can do G for growth rate. You can do whatever you want. But I like to think of A, B to the X, right? So I do know my X. It's the amount of time that's passed. It is 5, and we're dealing with years in this instance. Okay. So time is measured in years. So now I got to figure out what the heck these values are. I'm going to divide by 3,200,000. Cancels. Divide by 3,200,000. Luckily, I can cross off 1, 2, 3, 4 of the zeros, and I'm left with 42 over 320, which still is, it's going to be a pretty small decimal. That is not my growth rate, right? So I'm going to do, let's clear this out, 420 divided by 32. I get, oh, not 30. I am so sorry. It's 320. Let me clear that out again. Gosh, I'm wasting your time again. 42, right? 4 zeros cancel. There's still one here. 42 divided by 320. And I get, that's the decimal I was expecting, 0.13125 equals b to the 5th. Now I need to fifth root. I cannot do this problem without a calculator, folks, okay? It's all right to not know. This is like the real world, right? You're never going to have perfect fifth roots or perfect square roots, okay? You're often going to have to do some work. So I'm going to go to my calculator. I'm going to use the y square root x. I'm going to type in my x first, press this whole button, and then type in the y after. So I'm going to do 0.13125. I'm going to press that little square root of x to the with y being the index button, and then I'm going to type in a 5. And I get 0.6662233 and some other stuff. So we're going to approximate that to 0.67 equals b. So I get 0.67 is going to be my growth rate, and that falls right into what I was thinking, right? In order for it to be a decay, which it is because it went down, okay, it has to be between 0 and 1, and that's between 0 and 1. Makes sense. I'm feeling good. So that means my equation is going to be y equals my initial amount, 3, and if you put 3.2 million, that's fine, but if you're calculating, you really want to make sure you have it modeled as the actual number it is, with a 0.67 growth rate, raised to the x amount of years, okay, years. Let's double check and see if that's right. It is. They kept everything in terms of millions. I would be fine, like I said, if you did that, or if you kept it as actual millions. If you keep it like this and you plug in, for example, 100,000 here, you would have to put 0.1 because 100,000 is 1/10 of a million. And if that's tricky for you, then you should have it like this. Both ways are correct. So let's look at going through and solving our part B now. Now that we have our function that's going to model this exponential decay, let's figure something out, okay? How many cans made of recycled aluminum can be expected in the year 2050? We're not going to plug in 50. Remember, our starting year is 2000. Sorry about that. Our starting year is 2005. So how many years has it been to get to 250? 45. So I'm going to use my equation like this because I like it. I'm going to put y equals 3,200,000 times our growth rate, or it's really a decay rate, kind of, right? And then instead of x here, or instead of 5 here, I'm going to put in 45 because that's how many years it will have been. And now I'm just going to make sure to grab my calculator again and figure out what I got going on. So I'm going to clear it out. I have 0.67, and I'm either going to use my caret button and press 45, or I'm going to use my x to the y button and then press 45, which gives me it gives me a small number, 0.1234567, 7 zeros and then 1 4. 5, 6, 7, and then a 1, and then a 4, and then a 9. So I'm going to round it to 1 5. That is a really small decimal. I'm going to keep that exact decimal in my calculator, and I'm going to times it by my 3,200,000 right now, and press enter. And I get kind of a small number here. I got 0.04769. Okay, so really that should be 0.48, and that's y. So really, like, can I have 0.04 of a can? No, because remember, they're saying how many cans will be made of recycled aluminum. I mean, I'd round that. That's none. That would mean that there are no cans that will be made of recycled aluminum. And that seems a little weird, but if it's going down, right, it's getting closer and closer and closer to 0 cans, right? There's nothing being added to this. So my assumption would be that maybe at that point it's pretty much nothing. Let's see. Nothing. Okay, so remember, they're going to either shoot up really fast, or this one's really going to get closer and closer and closer to that asymptote, and that asymptote's going to be at 0. So none. Okay. Now that might not necessarily be true, right? But if it continues at this exponential decay rate, then we will have none. It might not be the actual value on that specific year because things could change. Okay. You're going to have one problem in your homework. I think it's number 15, where you're going to have to write an equation by finding the growth rate and then actually do something with it. The other last four parts of your homework are going to have you look at calculating compound interest. And compound interest, it exists, okay? And if you've taken finance at all, you've seen this interest function already, okay? So A is going to be the amount you have after T years. So it's your outcome, okay? T represents how many years you have it invested. P is like your A value. It's what you start with. It's your initial amount or your principal amount. It's where you start. And then on the inside here, okay, it's 1 plus R, which is your annual interest rate. So if that you get 3% interest, you would do 0.03. Okay, that's your rate. And N is the number of compounding periods each year. So if they say it's compounded monthly, that means they can do this calculation every month. We would put 12 here and a 12 in for N. Okay. If they do it every quarter, that would mean they do it 4 times a year. Or if they do it annually, they would do it 1 time a year, and you would use those values for your N. So I know this is kind of tricky at first, but it makes sense when we start applying it. Okay. And you're welcome to reference your notes and or put this on that note sheet when you start thinking about preparing for that exam. Do not do it now. Making that sheet helps you review. So an investment account pays 4.2 annual interest. So it's happening every year, compounded monthly. If $2,005 is the amount invested in this account, what will the balance be after 15 years? So we're just going to plug pieces and parts in here, okay? We don't know what we have at the end. Our principal, or what we start with, is 2,500. We're going to times it by 1 plus, because it's going to increase, right? They're saying it pays this much, so it's going to be going up by that much. So 4.2 is our rate. Now, we can't just put 4.2 up here. We need to notice that it's a percentage, and in order to compute with percentages, we need to change them to decimals. So we'll move it forward 2 spots, which is what we always do when we're dealing with percentages. And we're actually going to use a numerator of 0.042 over N. And N, again, it's kind of weird, is the number of times that it's compounded annually, okay? So compounded means they're doing this actual calculation. They're doing this actual calculation every month. So how many times does that happen in a year? 12. So our N value is 12. So we'll have an N times T out here. T is always your amount of years, right? So we're going to put a 15 there. Now we just need to PEMDAS the bejesus out of this, okay? I'm going to start by doing 12 times 15. You know what? Maybe we should really follow like order of operations the way we should. We should start in our parentheses, right? And then do our exponent and then do our multiplication last. So let's start in these parentheses. I have addition and division. I have to do the division first. So I'm going to grab my handy-dandy calculator and I'm going to pull up and type in 0.042. So 0.042. And I'm going to divide it by 12 because it's going to be compounded 12 times. And I get 0.0035, 0.0035, and I'm just going to go ahead and add that to 1 right now. So this is 1.0035. Now this should always be a decimal value, folks, so that when you add it to 1, it's 1 point whatever that decimal is. Now, instead of rewriting both of these, I know I'm going to have to take this number and raise it to whatever power's here. So I am going to just do 12 times 15 right now, okay? So back on my calculator, 12 times 15 equals 180. So this means this is going to happen 180 times. If it's going to happen 12 times a month or 12 times a year over 15 years, that's 180 times that this is going to occur. And it's going to happen to this 2,500 we initially invest into it. So PEMDAS says this piece next, right? So I'm going to type in 1.0035. And I would love if you had a calculator and you're doing this with me. I'm going to press my caret button and then 180, or I'm going to press my X to the Y power button and then type in 180. And I get here 1.8755 blah, 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 blah. Okay. Now I'm not going to actually, I'm not going to actually press clear and retype that in. I already have it in my calculator. I'm just writing it for you so you can see, okay, my next step is going to be to times it by 2,500. And I get 4,688 point. And my question to you is, where should I round in this, right? We're dealing with money. We should round to the nearest penny. So it's 0.866, so it should be 0.86, not, well, it would be 66, but we're going to round it to the nearest penny, so it's going to be 0.87, okay? So this is pretty sweet. Think about that. If you have $2,500 and you're said, hey, you know, take this money if you don't need it for a little bit, invest it in this account, just let it sit there, okay? In 15 years, it could almost double, okay? So just by having this money invested in an account for 15 years, specifically an account that is 4.2% return, compounded monthly, I would make $4,680.87. I mean, not profit, but I would be making $2,188.87, okay? Just by letting it be in an account and not touching it. And that's how interest works, whether it's interest that you're getting or interest that's being compounded on a mortgage or a car payment, okay? That's how they make their money off of you. So I want you to give a go to the second one, okay? And there's the formula. Hopefully you have it written down. I'm going to scroll down. You might not be able to see it. Give this a go, and then I'll solve it, and then we're done for today, okay? And you'll be able to start your homework assignment. All right, folks, let's take a look at this one, okay? So first things first, I took my, and you can see that matches. Whew, I like to check it too, just to make me a little less nervous. I get nervous just like you guys do, okay? That's why I like to give you those answers so you know if you did it right. So I took my compound interest, okay? It says compounded, so I know I'm doing compound interest, and I plugged stuff in. So I said $100 is my principal or my initial amount. I started here. Then I have to figure out my growth, right? 1 plus my percent divided by how many times a year it's going to happen. So my percent, boom, boom, move it forward 2 spots, 0.012. Okay, so it's really only like a 1% increase. Divided by 24, because it's happening 24 times in a year, twice a month for a whole year. Then I brought that n value out here, because remember, it's n times t, so it's 24 times the 20 years invested. Next, I went and simplified inside my growth here. So it's 1.00005. I think I said an extra O, but I didn't write an extra O. Then I multiplied these two things together to get my 480. So I took this growth factor, which it is bigger than 1, right? So it is growing, but very, very, very slowly. And I raised it to the 480th power because it's going to be compounded 480 times if it happens 24 times a year for 20 years. So after I raised this to the 480th power, okay, on my calculator, I got 1.27, blah, 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 hot mess, okay? I kept that exact number on my calculator and I times it by 100. And it brought me to 127.11 and something that made me round this up to 0.12. Okay, so here's the flip side. So this one I had less money invested. And it was a smaller percent, right? It was only like 1.2%. Up here, it was 4.2%. So it was a lot higher. So after 20 years, it only made $27. Now, I'm saying it, and you're probably like, oh, yeah, only $27. Why bother? Well, think about that for a second. This is $27. That's 25% of this 100, right? A little bit more than 25%, maybe 26 or 27%, right? That's actually 27.12%. But anyways, that's not too bad. I mean, if you invested $1,000, that would be $270. If you invested $10,000, that would be even more. And every time it's just multiplying by more and more and more. So the more you can initially invest, even with a smaller interest rate, the bigger you'll end up with at the end. Okay? So, food for thought. You do have a handful of these. You're just kind of plugging in and simplifying in the correct order. Feel free to reference your notes. As always, I have office hours, so feel free to show up for office hours 1 to 2 if you need to. I will make sure to post the link. Okay, folks? And if you have any questions in between now and then, feel free to email. I will talk to y'all later. Bye.